let's take a look at differentiation. There's a lot of stuff in this section, but hopefully we don't have to spend too much time reviewing it. There's gonna be a lot of writing if you're copying these down. But the first thing that I want to talk about is the limit definition of the derivative. This is the one where you take the limit of the difference quotient. It has the f of x. Well, I'll write them down. You have the derivative, so all of these are the derivative, and the whole idea of this is if you see something that looks like this form, you don't actually have to evaluate the limit. It could be a complicated limit. You don't actually have to evaluate the limit. You just have to know, wait a minute, that's the derivative. So that's what's going on here. So if I had something like find the limit as h approaches 0 of, I think this was one of the problems, 8 to the 1/2 plus x, yeah. Wait, it'd be plus h. So if I had something like this, I think this was on a review, and I'm trying to find this limit, this is the difference quotient, and it's this. It's like this is the difference quotient. We're taking the limit of that. That means it's the derivative of something. So what is that something? F of a? Well, that's just 8 to the 1 or times 1/2 to the 8th power. So here we could have, I know that f of x would be equal to 8 times x to the 8th. How do I know that? Well, I'm just comparing these two and I'm trying to figure out what's the same between the two. Well, I have the 1/2 part, and if I know this difference quotient, I know that a would be 1/2. Then I have the plus h. So instead of actually evaluating this limit, I could actually just take the derivative, f prime of x, and plug in 1/2. So I would have 64 x to the 7th, right? That's using the power rule. And I would evaluate that at 1/2 because that's what a is. And I could figure that out. So that's the difference quotient. It's super important to have those in your head so that you can get these problems real quick and then move on. The whole idea of the derivative is that it's the slope of the tangent line to a function given a certain x value. So it's the slope at one single point, but it comes from the slope of the secant line. So it's important to remember the slope of a secant line or the average rate of change, because this will come in handy when you're approximating something. That's why we have something that kind of looks like a slope. This is the slope or the average rate of change, so it's important to remember that. If you're thinking about problems in context, then you might want to use the average rate of change for something. But we have the slope of the secant line is related to the slope of the tangent line. That's how we get those difference quotients, the limits of them. So if we're talking about the secant line, then we also got to talk about the tangent line. So the derivative, if the slope of the secant line is considered the average rate of change in context for whatever you're talking about, then the derivative is the instantaneous rate of change. That's what we can get. So like if we're talking about a particle moving, it has a position function, and the derivative would be the velocity function. Then you could use the secant line between 2 points and find an average rate of an average velocity. But if you wanted an instantaneous velocity, you'd have to use the derivative. So there you go. It's also important to remember just from graphs that sometimes you don't like the derivative doesn't exist at certain points, and that happens at all discontinuities. So we have any type of infinite discontinuity or jump discontinuity, or if there's a hole, then the function's not differentiable. It's not defined at those. For some cases it's not defined. Like here, it's not defined at this whatever x value this is. But if there's any type of discontinuity, you don't have a derivative there. At cusps or corners, you don't have a derivative, and at points of vertical tangency, Technically, you don't have a derivative there either, but we know that they tend towards vertical tangent line, or sorry, a slope, like an infinite slope. So we can actually still describe the tangent line for this stuff, but it's technically not differentiable there. So if you're doing something with critical points and you find out that the derivative doesn't exist, you might want to check to see if you have a vertical tangent line, which means for the derivative, the bottom goes to 0. Maybe take the limit from both sides, because if you have the limit of the derivative of the function and it's approaching, this looks like, what is that? It looks like well, it's definitely negative, and it's getting like infinitely negative, so negative infinity. If you approach from the right side, that's still a negative slope, and it's approaching negative infinity. So, I mean, it agrees on both sides for the limit, so you can say that it has a vertical tangent line there. Also, know all the trig and inverse trig derivative, actually all of the formulas that we've been trying to memorize. Those are super important. Those are the easy questions, and you want to get the easy points. So it just helps to memorize those. No matter how hard the multiple choice is or easy it is, they're all worth the same point. So might as well get the easy ones for sure, and that go quick. That way you have more time to work on the hard ones. These ones should be easy. If you just remember the derivative formulas, then you should be good with that. I think I'm going to end this video and start another one for the next part.